Hi, in this video, let's look at how to use various programming languages or frameworks in Hadoop. Applications in Hadoop can be written in a wide range of languages. Depending on the use case, the developer can choose an appropriate processing engine as well as an appropriate programming language. Some problems may require a procedural approach or a functional approach. Scripts in a high-level languages such as Pig and Hive are automatically combined or compiled into a set of MapReduce Java classes by the respective engines, which are then executed on the Yarn framework across a cluster. Yarn is yet another resource negotiator, which we'll look in the next video. Pig is a simple procedural scripting language in which the developer defines how data is transformed from one step to the next. Hive uses Hive Query Language, or in short HQL, which is similar to the SQL. We will talk about more on Pig and Hive in various different videos. As the developer can choose an appropriate processing engine, this gives the developer a greater flexibility in dealing with complex problems. Tools such as Storm and Spark are often used for processing data intensive applications, which may involve interactive or analytical approaches. These engines provide support for multiple programming languages. Now let's quickly look at different types of processing frameworks we have in Hadoop, starting with batch processing. So batch processing is used to process data in batches, and it reads data input, processes it, and writes it to the output. Apache Hadoop is the most well-known and popular open source implementation of batch processing and a distributed system using the MapReduce paradigm. The data is stored in a shared and distributed file system called HDFS, or Hadoop Distributed File System, where the data is divided into multiple splits, which are the logical data divisions for the MapReduce processing. To process these splits using the MapReduce paradigm, the map task reads the splits and passes all of its key value pairs to the map function and writes the results to the intermediate files. After the map phase is completed, the reducer reads intermediate files and passes it to the reduce function. Finally, the reduce task writes results to the final output files after applying the relevant logic. The advantages of the MapReduce model include making distributed programming easier, nonlinear speedup, good scalability, as well as fault tolerance. The disadvantage of this batch processing model is being unable to execute recursive or iterative jobs. In addition, the obvious batch behavior is that all inputs must be ready by map before the reduce job starts, which makes MapReduce unsuitable for online and stream processing use cases. Moving on to the stream processing. So stream processing is to continuously process and act on the live stream data to get a specific result. In stream processing, there are two popular frameworks. One is the Storm, which you can find it on storm.apache.org. It's from Twitter, and S4 from Yahoo, which can be found on incubator.apache.org/S4. Both the frameworks run on the Java virtual machine and process keyed streams. In terms of the programming model, S4 is a program defined as a graph of processing elements, small subprograms, and S4 instantiates a PE, or a processing element, per key. In short, Storm gives you the basic tools to build this framework, while S4 gives you a well-defined framework. Moving on to the real-time processing. Real-time processing is to process data and get the result almost immediately. This concept in the area of real-time ad hoc queries over big data was first implemented in Dremel by Google. It uses a novel columnar storage format for nested structures with fast index and scalable aggregation algorithms for computing query results in parallel instead of batch sequences. These two techniques are the major characteristics for real-time processing and are used by similar implementations such as Cloudera Impala, Facebook Presto, Apache Drill, and Hive1Test powered by Stinger, whose effort is to make 100 times performance improvement over Apache Hive. On the other hand, in-memory computing no doubt offers other solutions for real-time processing. In-memory computing offers very high bandwidth, which is more than 10 gigabytes per second, compared to hard disks 200 megabytes per second. Also, the latency is comparatively lower, nanosecond versus milliseconds, compared to the hard disks. With the price of RAM going lower and lower each day, in-memory computing is more affordable as real-time solutions such as Apache Spark, which is a popular open source implementation of in-memory computing. Spark can easily be integrated with Hadoop, and the resilient distributed dataset or RDDs can be generated from the data sources such as HDFS and HBase for efficient caching. In summary, real-time frameworks provide near real-time processing for data in the Hadoop ecosystem. They can be built on top of generic frameworks such as Spark Streaming or Spark, or as a standalone or a special purpose framework such as Storm. Apache Spark offers unique in-memory capabilities and is well suited to a wide variety of data processing workloads, including machine learning and micro-batch processing. Moving on to the graph frameworks. So here we have Giraffe, GraphX, and GraphLab, which are popular graph processing frameworks. Apache Giraffe is a library that runs on top of MapReduce. Giraffe originated as an open source counterpart to Brigal, the graph processing architecture developed at Google and which was described in 2010. GraphX is a library for graph processing on Spark, whereas GraphLab was a standalone special purpose graph processing framework that can now also handle tabular data. Moving on to the machine learning frameworks, we have Mahout, MLlib, Oryx, and H2O, which are commonly used machine learning frameworks. At a high level, Mahout is a library on top of MapReduce, although there are plans to make Mahout work on Spark. MLlib is a machine learning library for Spark. Similarly, Oryx and H2O are standalone special purpose machine learning engines. The way in which these different frameworks or languages are integrated into Hadoop is shown in this picture. Big Hive scripts are compiled into MapReduce jobs behind the scenes. In the latest versions, these can be compiled into test job. Then these MapReduce or test jobs will run on Yarn framework of the Hadoop cluster. We will have a deep understanding of Yarn in a separate video. Applications can be written in Scala, Storm, Spark, and these engines can plug straight into Yarn framework. To provide greater flexibility to the developer or to the analyst to provide different ways of processing for different applications. As we've seen already, many applications can run at the same time in the same cluster, even if they are written in different engines. We have seen how to use different languages or frameworks in the Hadoop ecosystem. In the next video, we'll discuss primarily more on the Hadoop architecture and the most important daemons or processes that form part of the architecture. If you enjoyed this video, please subscribe to the channel for more upcoming videos.